So we're going to start off by asking the question, what are combined or compound structures? What is it we mean when we say we're dealing with a combined structure or a compound structure? So when we're learning about structural analysis, at the start, we usually break structures up into two different camps. We say we have a structure that is subject to axial loads, okay, and that's typically a truss type structure. Or we say we're dealing with a beam or beams and frames, and those are structures that are developing bending moments and shear forces in response to external loads. So they're the two different camps. So let's start off by just getting down on paper a couple of key points about these two different kinds of structure. So we'll start off thinking about axial forces and structures that resist external loads via axial forces. In a truss, our members resist tension and compression, typically, or they have no force in them. They're connected at hinge and pin joints, which are free to rotate. So that's a key point. The members that join at a hinge are free to rotate relative to each other. There's no bending, so our analysis models typically assume that there is no bending in the members of a truss, and all external loads are applied at joints or nodes. Okay, because if we had an external load applied in between two nodes or two joints in a truss, then we'd get bending, local bending in that node, and our simple truss model would no longer apply. So we can say we have, just to get a couple of points down here on paper, so we have a nice record of what we've been discussing, we can say that the members resist tension or compression. They're connected at hinge or pin joints, which means they're free to rotate. That is free to rotate relative to each other. There's no bending. And all external loads are applied at joints or nodes. Okay, so what have we said? We've got 4 different bullet points here, and all we're saying with these bullet points is these are typically the assumptions that we make when we model a truss structure using our simple truss models. So let's just get a quick example down here. Okay, so we have a force on the end, P, and it doesn't take too much brain power to work out that that's going to put this member into compression and this member into tension. Okay, so hopefully if you're taking this course, you've looked at that and that's reasonably straightforward for you. So all we're saying here is that we have a simple truss. To analyse this simple truss, we could, if it wasn't so simple as this, if it was a truss that had more members, more nodes, we could use, if it was a statically determinate truss, we would use something like the joint resolution method or the method of sections. If we wanted to analyse a statically indeterminate truss, maybe, or perhaps we want to work out the displacements within that truss, the deflections at different points, we might use something like the virtual work method. Okay, so now that's the first type of structure, and when you're learning structural analysis, that's typically the starting point. You start off with something simple, like analysing a truss. Then we tend to move on and we start thinking about beams and frames. And beams and frames are members that are primarily subject to bending, so bending and shear. Alright, so internal bending moments are typically used here to resist external loads. So what do we mean by that? An external load would come onto a beam, be applied to a beam, let's say for argument's sake, and that beam will respond by developing stresses internally within the beam, and the resultant of those stresses would be a bending moment and indeed a shear force. And so that's what we say, or that's what we mean when we say that a beam would develop an internal bending moment and shear force in response to external loads. In a frame structure, we would have moments transmitted through the joints, which is obviously different to a truss where there's no moment transmitted between members at a joint. And typically we ignore the influence of axial load. So we ignore things like axial shortening of column elements in a frame structure because the axial shortening tends to have a negligibly small effect on the behaviour of the structure as a whole. So let's get a couple of bullet points down here on that. Okay, so what are the simplest examples? A shear force developing internally, which we could represent with a shear force diagram, which in that case would look like that. And we'd also have a bending moment developed internally, and we could represent the change in that bending moment across the structure with a bending moment diagram, like so. Okay, so that's the other type of structure that we're talking about. We could also expand that a little bit and think about a frame structure. So instead of a simple beam, imagine we have a very basic 3-member frame. And I won't draw the shear force diagram in this case, but the bending moment diagram for this would look something like this. Okay, so all straight lines in our bending moment diagram. Important point here, there is a moment transmitted through that joint. So that's a joint between the horizontal and the vertical member. And what we're seeing here is that there is a moment transmitted at that joint. And the other point I made was that we typically ignore the effect of the influence of axial force in columns. So obviously that column will experience a compression force, and we usually, for the purposes of a simplified analysis, we ignore axial force in the columns. And once again, we do that because the influence or the effect of that axial force on the overall behaviour of the structure pales in comparison to the influence of that point load applied to the structure. Okay, so far we've summarised the two different camps or the two different kinds of structure we typically analyse, or we typically take a real world structure, and if we can, we say it's either a truss type structure, in which case we apply a simple truss model, which you've seen here, or we would say, well, that structure is definitely going to be developing bending and shear, and so I'm going to have to model it as such, and in that case you would model your structure as a beam or a frame structure. Now this course is all about, what about those real world structures that fall in between two camps? What about those structures that they have bending in them, but they also have members within them that are subject to axial force, and that's what we call a compound structure or a combined structure or a complex structure. So it's a combined or a compound or a complex structure simply because it combines members that experience bending and shear with members that experience only axial force. And those kind of structures are much more common in real life than a pure axially loaded structure or a pure bending type structure. So a good example of a compound or a combined structure, I'm just going to call them complex structures from here on, but a good example of a complex structure is the cover image of this course. Okay, so let's take a look at this structure here, right? Let's give it a title first. So this is a complex structure. Right, what have we got? We have a beam structure. Let's just put some supports on this so it starts to make a bit more sense. Let's imagine it was supported here and it was supported down here. So it's a beam spanning between those 2 points. We'll call them points A and points B. And you might have seen this. I know I've seen these kind of structures in, if you walk into a large supermarket, very long spans in the roof, you'll often see things like this where you've got a beam which looks like it's acting like a normal beam, but to support that beam, to help that beam out, we have a truss below the beam. So what you essentially have is two different kinds of structure, a truss structure and a beam structure, acting together to resist whatever the load is. And let's assume there was some loading on this like so. Okay, so the beam is obviously going to be bending, but naturally enough, there's going to be some forces transmitted into those black truss members as well. And so the beam, this combined or complex structure, is going to do a better job of resisting the loading than the beam would on its own or a truss would on its own. And the whole purpose of this course is to give you the strategies that you will need to analyze, to do some simple analysis to work out exactly what's going on in a structure like this. So analyzing the structure, working out internal forces and bending moments, because then you can go ahead and you can design a structure like this. So that is what we mean when we say a complex structure. So let's just get a couple of notes down on that. Typically, we would say complex structure is characterized by a beam and in this case a truss, but a beam and an axially loaded member acting together to resist external loads. So to make that more general, I'll just say bending and axially loaded members act to resist external loads. So typically these structures are statically indeterminate. So we're going to make use of two basic principles to analyze these structures. We're going to use the principle of superposition and the principle of virtual work. So by the end of this course, you'll be able to apply those two principles in a very flexible way to be able to analyze complex structures just like this one. You'll be able to determine axial forces in the axially loaded members. You'll be able to work out what are the bending moment and shear force diagrams for the bending members. And you'll also be able to work out unknown displacements. So you'll have the full toolbox to be able to tackle a structure just like this one.